Okay, we continue our our paper by okay. Now we have D. We have the domain xy belonging to R square, such that 0 is smaller than y is smaller than 1 and 0 is smaller than x smaller than root of y. Okay, and let f from R2 to R2 be the vector field defined by f of xy equal to x over 2 and x. Then the work made by the function f along the boundary of the domain, okay, counterclockwise or assuming a counterclockwise orientation is okay. So typically you have so look, please look that they gave you the domain D, but they want the work on the border of the domain. Okay, so you don't even know you know the domain, but you don't know the you don't know the boundary. Okay, so basically this is an application of the Green theorem, right? Suppose that, what does the Green theorem say? Suppose that you have this is your domain. Okay, let's call it omega. So in fact, you know, in this exercise is D. Let me call it D, like in the exercise. Okay. So this is the domain D. Now, and actually this is the border of, here is the border of D. Now, actually, you can say that the border of D is a curve, right? And it is possible to integrate a vector field on a curve. So, what the Green theorem says that the integral, okay, the integral of a vector field on the border of the domain, when you are working on the border, we use I don't know what the notation you use, but I think you also use d gamma. What does it mean? The tangent vector, because we are moving at each point. This means the work, yes or not? This means the integral of the vector field on the border of the domain, and this is the integral of the vector field on the curve, yes or not? It's actually equal to, please remind that your vector field will have two components, the x component and the y component. So if you don't, this is just telling you that instead of doing the integral on the border of the domain, and that the integral of the vector field on the border of the domain is actually equal to the integral of something inside the domain. Okay, it's actually equal to the integral inside the domain. Look at the difference. So from one side I have the integral on the border. So instead of doing the integral on the border of the vector field on the border, I can just do the integral of this function, the derivative of fx with respect to y minus the derivative of fy with respect to x inside the domain. Is that clear, the paradigm? So from one side we are saying that the integral of the field on the border is equal to the integral of this stuff in the inside the domain. This is the meaning of the Green theorem. But pay attention that look, where in analysis 1, when you have an interval from A to B, there is only one direction, right? You move from the smallest number to the biggest. But when you have a domain like this one, a border like this one, What is the problem? The problem is that one can move on the border counterclockwise or clockwise, right? Or clockwise. This means what? This integral, so this way, when you compute the integral in this way, so when you compute this integral in this way, you are moving in the domain. So this assume that you choose you are moving in such a way that the domain is at your left. Okay, this way, if you compute in this way, you are moving such that the domain is at your left. But typically, most of the domain, so I will not even try to do, because most of the domain they give you I like that. Okay, so basically when you are moving, except maybe if I give you a domain like this one, now the domain is just this, yes or not? I wanted to just say that when you are moving, normally when you have for normal domains without holes, when you are moving on the to have the domain on your left, you should move clockwise. Yes, in this case, if you want to have, so if you do this integral by using this formula, you will integrate out clockwise. This will be clockwise, clockwise, but here you should be moving. Yes or no? Here is inside you move clock, and outside you move counter. Yes or not? So the Green theorem is not good to compute if you want to find. If somebody asks you to find the work of a field on this domain, and he say always move counterclockwise, the Green theorem will not give you the right answer, because the Green theorem will do it like this, counterclockwise outside, but inside it will be clockwise. Is that clear? But that's why usually students are, if you can do it, please represent the domain before applying the Green theorem, just to make sure that there are no holes or stuff like this. Okay, the domain we have in this case is not so that difficult to represent, but I repeat, I don't use to represent the domains because typically in an MCQ, I mean, the probability to give you the domain like this one, yes, it is possible to give you the domain like this one, but in this case, when they give you the domain like this one, do not use the Gauss, because this kind of domain, it's to say that, for example, x squared plus y squared should be between 4 and 9, right? And this is, I think, except this case, I see very hard to have another case in which. Okay, so so typically they want you to know how to apply the Green theorem independently to complications. So also in this case it's the case. So to get the integral of the field on the border, okay, we will say that it is equal to the integral on omega, because we know the domain, of df of the derivative of fx with respect to y minus the derivative of fy with respect to x. Okay, and note that we are performing good because I told you that this typically leads to the counterclockwise orientation. Is that clear? So what is the what? No. The question of my students if this is related to the divergence. No, later we will see the divergence of a field. We speak about divergence of a field, not divergence of x. Okay, you have a vector field and we speak about the divergence of that vector field, but this is not yet the divergence. Okay, so for our exercise, let me repeat what is f of xy. Going back to the f of xy is x over 2 and x, right? F of, let me change the color of the pen. F of xy is x over 2 and x. So the derivative of fx with respect to x, what is fx? Fx is this one, right? And this is fy. Now we need to do the derivative of fx with respect to y. That will be 0, right? The derivative of fy with respect to x will be 1. So at the end, what do we get? We get that the integral that we want will be the integral on omega of the derivative of f with respect to y, which is 0 minus 1. Yes or not? In dx dy. Now it gives you, they gave you omega, right? They gave you omega very easily. It was from 0 to 1 and then from 0 to y, right? So it's the integral from 0 to 1, then integral from 0 to y of minus dx minus root y, yes, dx dy, right? Then you just do the computations. Excuse me. The computations are then equal to, I can take out the minus because, by the way, so minus the integral from 0 to 1 of now of the integral from, I mean not the integral, when I integrate this will be the integral of it will be x taken between 0 and root y, right, in dy. Then this gave us integral from 0 to 1 of root y in dy. Okay, it's like the minus the integral from 0 to 1 of y to power half in dy equal to y to power half plus 1 over half plus 1 taken between 0 and 1 minus, right? So it's y to power 3 half over 3 half taken between 0 and 1. Now is 2 over 3 multiplied by y to power 3 half is square root of y cube, right? Doubts? Gave you minus 2 over 3, right? Okay, if we didn't do any mistake, there should be the answer. No, we made a mistake somewhere. He needed clockwise, or no, it was counterclockwise, right? So we made it correct, but why did I have, let me understand, where did I make a mistake? So I think the theorem is exactly like this: the derivative of x with respect to y minus, let me check the field, because I have 2 over 3 but not minus 2 over 3. The field is x over 2x, yes. The derivative will be no, I am afraid that it's the derivative of fy with respect to x it's like this. The derivative of, because it's like this, it's like you take the derivative with respect to x, derivative with respect to y, okay, and you put them, and then you put fx and fy, then you do the determinant. You see, it is first the derivative of x with respect to, is the derivative of f of y with respect to x minus the derivative of f of x with respect to. Is that clear? So here it is, there is a, I mean, the Green theorem should not be like that, like I said, but it should be the integral on omega of the derivative of f of y with respect to x minus the derivative of f of x with respect to. Is that clear? So there is a permutation here, and if there is this is 1 minus 0. Doubts? And so this minus disappear, it disappear, it disappear, it disappear, it disappear, disappear, and disappear. So the answer is 2/3. Okay, is there doubts? So how do you keep it in mind? Keep in mind that the field is f of x, then f of y. So I mean, to keep it in mind, you do the derivative with respect to x first, then derivative with respect to y, then you have the field which is f of x and f of y. You compute this like the determinant. So it's the first derivative of f of y with respect to f of x, then the derivative of f of x with respect to y. Is that clear? Okay, by the way, the answer I think is 3C. If you want me to write it better, it is the derivative of with respect to x and then derivative with respect to y, then fx fy. What does it mean? When you are doing it, is this times this, that means the derivative of fy with respect to x minus the derivative of fx with respect to y. So with this, we also review the Green theorem. Okay. So the answer is C. Now, question number 4. Okay. The surface integral. So we have to compute the surface integral. Let me clean the board. So we have the integral that is given by the integral of the integral of 3x plus 6y over 1 plus exponential of 4y, 1 plus exponential of 4y plus 4z squared, okay, in d sigma. So you are integrating this on a surface called sigma, and what are the data of the surface? The surface sigma is actually given by x, y, z belonging to r cube, such that x is between 0 and 1, okay. Then we have x minus 1 smaller than y smaller than 0, no, x minus 1, x minus 1 smaller than y smaller or equal to 0, and z equal to x, z equal to x exponential of 2y. So this is the, and we want them to compute the surface integral. Okay, so typically I always as usual like to, when I am doing, when solving exercise, remember, so at least for this first paper we will be solving by, let's say, by reminding a bit the theory. So when I have, what is a surface? Typically a surface typically depend on two parameters. Okay, so any surface depend on, you probably saw it in class, that a surface is a function of two parameter, u and v, right? And thus anytime I have a surface like this, I should try to represent it with, in the form sigma uv. Yes or not? The surface should depend only on two parameters. Anytime you have the surface, it should be, you should first represent it in the form sigma uv. Then once you represent the surface in the form sigma uv, keep in mind that a surface at any point has a normal vector, right? Then when I ask you to find the integral of a function on a surface in this sigma, what are the steps? Once you represent, so it will be the integral on u, then the integral on, so the integral on the first variable of the surface, then the integral on the second variable on the surface. Then I should put f, I put the surface inside the form. Is that clear? And then I multiply this by the modulus of the normal vector of the surface, and I integrate in du dv. So this is how you perform the integral of a function on a surface. So things to do: one, I should find sigma uv. So I should write the function like a function of the surface like a function of two parameters. Second thing I should do, I should compute the function. I should insert the surface inside the function. Third thing, I should find the normal vector of the surface at each point. Fourth thing, I should find the integral of, I should do f of sigma uv that I got before, multiply by the modulus of n. Is that clear? And last thing, I should integrate on u and v this product, f of sigma uv time n of uv, then the modulus of n of uv. Is that clear? In du dv. So let's follow the step. First step, we write the function. The easiest way to write the surface like the function of uv is to set x equal to u and y equal to v. Yes or not? Then you deduce that z, because if it's a surface, z should depend on x and y. If we go on this, and you can directly see from this surface that z will be v multiplied by exponential of 2 is u multiplied by exponential of 2v, right? Yes or not? So this is v. Doubts? Now, so what is the representation of the surface is sigma uv equal to u v and u exponential of 2v. Is that clear? So you got the first step. You have done with the first step. Now the second step is to do this, to compute the function at the to insert the surface inside the function. How do I do that? Here, look. So this means that this is my x, right? This is my y, and this is my z. So f of the surface just means that I take f of u v and u exponential of 2v. Doubts? So uv, these are all, it's just a matter of calculus. So what is f? At the place of x I put u, so to y I put v, the place of z I put this. So going up it will be 3u plus 6v, right? Divided by 1 plus exponential of 4v plus 4z plus 4. What is z? Z is, it will be plus 4u. It's 4 is u square exponential of 4v, right? So this is z square, 4z square. Now second step done. Now third step is what? There was a root here. Nice. It means that also here we have a root. Okay, thanks. Third step is to find n. And how do you find the normal vector of the surface? By doing the cross product of two things. Okay, let me write it here. So n, the normal vector of the surface, you find n by doing this cross product. You do I, j, and k, and then the vector that you have here is the derivative of all with respect to u, and the vector you have here is the derivative of all with respect to v. Is that clear? And you cross product the two vectors. So to get my n here, I just write I, j, and k, then and derive the three components of the surface with respect to u. Okay, it will be 1, 0, so I will get 1, 0, and the derivative of this with respect to u is exponential of 2v, right? Doubts? Now the last vector will be the derivative with respect to v now, so it will be 0, 1, and can you see the derivative of this with respect to v will be vu exponential of 2v. So it will be vu exponential of 2v. No. The derivative with respect to v will be 2. No, it's 2. No, I was making a mistake. Please, guys, if I make a mistake, you stop me. Guy. Okay. So it's 2 is going to, the derivative of this with respect to v will be 2u exponential of 2v, right? 2u exponential of 2v. Now I can compute my n, my normal vector. N is going to be I multiplied by, when I take I cancel and cancel, it become just exponential of, no, minus exponential of 2n. Okay, then when I take j, okay, it gives me minus j into, yes, 2u, yes or not? Then finally I cancel, like and then plus 1, right? Plus 1 times k, because this is, because if I cancel for k and cancel, it gives me plus k, right? So this tell me that my n has components minus exponential of 2u, comma, minus, okay, so this was, my student is telling me that this was v, this is v, so it is going to be 2u exponential of 2v and comma 1. Now look that, then we need to find we need to do the function multiplied by the modulus of n. So I need the modulus of n, right? So the modulus of n is going to be square root of this square, that means exponential of 4v plus this square, that will mean 4u square exponential of 4v plus 1. Yes or not? So now next step is to write the function. So this is the another step, at sigma uv multiplied by the modulus of n. Okay, so the function was, you have to be patient with 3u plus 6v, 3u plus 6v over the square root of 1 plus exponential of 4v plus 4u square exponential of 4v, 4u square exponential of 4, yes or not? Then I have to multiply by the modulus of n, right? That is going to be, the modulus of x is exponential of 4v, yes, plus 4u square exponential of 4v plus 1. So what do I see? I see that fortunately this and this can cancel, and I got that the function at this point sigma uv multiplied by the modulus of n is just equal to 3u plus 6v, right? Last step is then this, I also perform this step, and now I just need to integrate, yes or not? So finally the integral will be equal to the integral on u and the integral on v of the 3u plus 6v in du dv. But what are the limits for u? If you go back in the at the beginning of the exercise, they told you that x, that is u, so u is between, yes or not, and v is between u minus 1 and z. So this means the integral from 0 to 1 for u, and then from u minus 1 to z to 0 of 3u plus 6v in du dv. Is that clear? First, we'll first do in dv because we are, yes or not, and then in du. Now I give the integral from 0 to 1. Doing it in dv, it gets of 3uv plus the integral of 6v is 3v square, right? Taken between u minus 1 and 0, then du. So it gave us the integral from 0 to 1 of, if we put 0, it is 0. Then if you put u minus 1, it will give us minus, because, yes or not, it's going to be 3u multiplied by u minus 1 Remember that we are doing the substitution of v plus 3 u minus 1 square, right? In du, you take your calm and you expand, it gives you the integral of minus, there will be 3u square minus 3u plus, it will be 3u square, then it will be, because it will be u square minus 2u, so it will be minus 6u, right? And plus 3 in du. Okay, so it gives you the integral from 0 to 1 of 3u square and 3u square cancel. You have minus 9u plus 3, right? Okay. Yes. Excuse me. In fact, then thanks. So I was saying that 3u square plus 3u square, we have 6u square, right? So we have minus 6u square, then minus 3u minus 6u is going to be minus 9 plus 9u and minus 3, right? So finally it gave you minus 6 over 3, it's 3u, it's 2u cube minus 2u cube, right? You are plus 9 over 2 u square minus 3u. So just doing it at 1, it will be minus 2 plus 9 over 2 minus 3. So it's minus 5 plus 9 over 2, which is half, which is minus half. Okay, let's go and see if we didn't make any mistake. So the answer is B. Okay, we also stop here with this video and we continue in the next recording sections. Thank you.